Log on, tune in, find out. Another good idea from Cambridge.
And it's about polarization problems.
Thank you very much, and I would like to thank the organizers for inviting me here as well. So the main question is the following, that assume that H is a Hilbert space, and let's say that we are given n unit vectors in H, and I will just use u1 up to un, so they are unit vectors, or it is maybe better to think of them as directions. And the question is that we would like to find another unit vector v which is close to these directions. So close to all of these. Now what does it mean that this direction is close? Well, we are in a Hilbert space, so we can just take the inner products, and the most natural way to bound this closeness is to give a uniform lower bound for the absolute values of these inner products. Yeah? So the basic question is this, that if we are in a Hilbert space and we have n unit vectors, then what is the best constant that we can guarantee so that for any unit vectors there exists a further unit vector such that all of these inner products are at least C. And the relative of this question was raised in the 1930s, and that is called the Planck problem. And as it turns out that C equals 1 over n is always a valid choice, so it always works. Always works. So that is basically the content of Bank's lemma, which was proved in 1953 by Bank, that if we take these unit vectors u1 up to un basically as coordinate directions, and after that we are looking for the vector v in the form sigma epsilon I ui times 1 over n, where now these epsilon i's are plus minus 1. So we are just looking for the vectors in this form. So now if we choose v with maximal norm, among these 2 to the n choices, among these 2 to the n vectors, then it is true that the inner products of ui and v is at least 1 over n for every I. Okay. So we can always guarantee a unit vector such that the inner products are at least 1n. And actually, this is asymptotically as good as possible. So asymptotically good, asymptotically sharp. Because if I take my unit vectors just to the two-dimensional unit circle, well, rather on the half circle, so this will be the collection of the ui vectors. So I can write that ui is, well, now if we are the complex setting, it should be just e to the I pi, or uj is to the I pi j over n. Then it is easy to see that wherever I am taking a unit vector, there will be always one from the chosen one such that the inner product is is sine of pi over n at most. And of course, if n is large, then it is not pi over n. So basically, this 1 over n is as sharp as possible. So now the question, can we improve on this? And of course, if we are in a real Hilbert space, then not really, because if I modify a bit this picture, then I cannot really do any better. But so now if we are in a complex Hilbert space, then it turns out that we can indeed improve a lot. And that is the complex Planck problem. Proven by Keith in 2001, that there always exists a unit vector V. I will not write unit vector, so okay. Such that all these inner products are at least 1 over root n. Okay, so instead of a linear bound, we get basically a quadratic bound, and this is again as sharp as possible. So this is the best that we can say about the uniform boundedness of the inner products. And around the same time, in 1998, Benitez, Sarantopoulos, and Tong, and also it appeared in the paper of Litva, Shekhman, and Millman, the following question came up, that now if I do not want to estimate all of the inner products uniformly, but I would like to estimate their product, then what can we say? So that was in 1998. If we take the product of these inner products, UIV, then what can we say about this? Well, so for symmetric reason, it is better to take the nth root of this absolute value. And so now, just from the Planck problems, we see that there always exists a unit vector. So if H is real, there always exists a unit vector such that this is at most 1 over n to the n. And if H is complex, then let's just write it here. Then this is at most n to the minus n half. Oh yeah, sorry. Okay. And so actually this theorem was proved in 1998 by Arias de Reina, so 3 years earlier than his complex Planck problem, and his proof used basically an averaging argument on the unit sphere, and after that in 2001.
Don't you mean the opposite inequality? Larger than 1 over?
Yeah, sorry. Hopefully no more mistakes here. So I made a mistake because it will be better for us if we actually take the reciprocals of these inner products, and after that we will just have an upper bound. So now this was proved by Arias de Reina originally in 98. So the question can be, and this is actually sharp because if the UI form an autonomous system, then we cannot improve on this bound. Question, is it possible to improve on this bound here? And of course, one first checks the counterexample for the Planck problem. And it turns out that in this case, the this bound can be much improved. And after that, one checks the orthonormal system, and it turns out that then one has 1 over root n as well. So that's what became known as the polarization problem, or the real polarization problem, such that if we have these unit vectors in Rn, then there exists a unit vector v such that this is at least 1 over root n. Okay, so in other words, we have the same estimate regarding the product. We have the same estimate for the complex and the real Hilbert spaces. Well, so now, of course, it is just part of a more general question, namely that for each v, we can just take the sequence of these inner products. And actually, it is better to take the sequence of the reciprocals of the inner products. And now, just for the moment being, let's denote it by this P of V. And now, the Planck problem asks for estimating the L infinity norm of this sequence. Whereas the polarization problem that asks for the estimation of the zero norm of this sequence. And so now, of course, for every p, we can ask what is the best bound for the LP norm. So we can just consider the quantities 1 over n times sigma 1 over UIV inner product P, I think the 1 over P. Yeah. So we just take the LP norms, and question, what can we say about them? What is interesting? Now, if you do not take the reciprocals, but you just take the LP norm of the sequence that you get from the inner products, then in the 1998 paper of Litvak, Shefman, and Milman, it is well described asymptotically. But so now for this reciprocal sequence, we don't really know anything about the behavior except for some special cases. And now the question is that, of course, well, if the conjecture is true, then for real and complex Hilbert spaces, for p equals 0, we get the same estimate. For p equals infinity, we get a different estimate. So now that is what is the critical p? What is the p for which well, things work quite nicely? And of course, the most natural guess would be p equals 2. And indeed, this case is interesting for some geometric reasons that I will describe in a second. And now, the p equals 2 case is called the strong polarization problem. Which was first investigated by Peter Frankel and Keith Ball in 2007. Say. So why is this p equals 2 case interesting? Well, if I consider the polarization problem and I'm looking for extremal vector systems UI, so the vector systems which really give the reason why this constant cannot be improved, then the conjecture is that for the real polarization problem, the only extremal vector systems are the orthonormal systems. So for let's call P polarization problem, the only extremal vector system is the autonomous system. And it is also true for the Planck problem, for the complex problem, that the only extremal case is the autonomous system. But so now let's see what happens for the strong polarization problem. Well, so first of all, if U1 is orthonormal, then if we take this sum, then we know that it is just by the inequality between the harmonic and the arithmetic means. We know that this is at least n squared. So we cannot hope for anything better than n squared. So the conjecture is that this n squared, this is the extremal, or this is the extremal constant. Okay. But so now if we consider our counterexample for the Planck problem, so we take n unit vectors uniformly distributed on the unit circle. So we just take this ui into the uj into the I pi j over n. Then it turns out that there always exists a v such that this inequality holds, and this is the best possible. So in other words, if we consider this L2 case, then we get the same estimate if we have n unit vectors on the unit circle, and we get the same estimate if we have n unit vectors up in the n-dimensional space, which is very counterintuitive, because somehow you would think that if you are in the n-dimensional space, that you have much more space for finding this unit vector v, and therefore you would get a much better estimate. So now this is the first sign that this is indeed the most natural conjecture to work on. And so now the proof of this is not too simple. The trick is that when we are on the unit circle, just as I have written, then we can just work on the complex plane, and in fact, instead of taking the inner product of two real vectors, you can just take the distance between two complex vectors on the unit circle, and after that, this can transform that an analytic function is bounded by something. And now there are two proofs. One proof is, so the original proof that I made is using some equi-oscillation property, that if you are in an extremal case and if you see the modulus of this analytic function, then basically it will oscillate between the extremal values many times, and from them you can get a characterization result. And there is also another proof due to Erdélyi, and that is using the generalized Ballstein inequality in a quite tricky way. So now there are two proofs for it, and so this is this is the complex polarization inequality. So we have full-dimensional extremal cases, and we have a two-dimensional extremal case. And now it turns out that we have any-dimensional extremal cases, where any dimension is between 2 and n, because what happens, well, assume that the vector system U is extremal in R, say L, and another vector system U tilde is extremal in R to the K. Then if I just take the orthogonal sum, the direct sum of U and U tilde, then it turns out that this is extremal in in R to the L plus K. Okay, so basically we have extremal vector systems in any dimensions. So that is the motivation to work on this problem. And now, first question is, of course, how to find V. So somehow we would like to find a good unit vector V such that this holds. Well, so if we see the bound lemma up there, then it gives a hint that, at least in this case, V is constructed as if it was well, it is constructed as a linear combination of our vectors ui. And now the coefficients are just plus ones and minus ones. So now it gives the hint that maybe we can construct a V which is again a linear combination of these ui's. And it will be indeed true. So we will look for V in the form sigma alpha ui. And so now, of course, I would like to estimate these inner products or calculate these inner products VUI. And the question, how can I do it? Well, what would be the natural choice for our unit vector V? The natural choice would be the one for which this quantity is maximized. Minimized, sorry. Yeah. So that would be the natural choice for our unit vector V. But so now instead of that, we will take V for which the product of these the reciprocals of these inner products is, well, minimal or at least locally minimal. Now, what do we get? Well, just and of course the norm of V should be 1. Yeah. That is the original conjecture. Now I changed this a bit. I want the norm of V to be n. It's just a constant multiplier. So now I'm looking for a vector which has norm n, and subject to this condition, this product is locally extremal. Now what do we get? Just from the Lagrange multipliers we get that where the gradient vectors must be parallel, so the gradient vector of the norm is just V, so we get that lambda times V. And what is the gradient vector of this? Well, it will be just a sigma ui divided by ui v times. Yeah. So we get that this is true. And now what is this lambda? Well, if I just take the inner product with V both sides, then I
cannot see the ODC.
Oh, I see. So, is it better now? Okay, so it's very simple. So we just take the inner product, and after that we get that lambda times n equals, well, what do we have here? This is just n times this product, yeah? So we get that n cancels, and lambda is this. So now what do we get? Well, we get that V equals sigma ui divided by inner product uiv. Okay. So now this is true for all the vectors V for which this product is locally maximal subject to that condition. And now these coefficients will be our alpha i's. Okay. So now what do we get? We get that for these vectors, we get that for these vectors, v can be written in the form sigma alpha I times ui, and alpha I equals 1 over inner product uiv. Yep. So in other words, the thing that we have to estimate is sigma alpha L square. Okay. And there is another thing, that what happens if I take the inner product with j here, with uj here. Then on this side I will get 1 over alpha j, and on this right hand side I will get sigma alpha I ui uj. So now what does it mean? Well, this is just the ij entry of the Gram matrix created from my vectors u. So if M denotes this Gram matrix belonging to my vectors ui, then this equation just means that, and now if alpha is the vector alpha 1 up to alpha n, then this equation just means that M alpha is alpha inverse, but now the inverse is taken coordinate-wise. So this coordinate-wise. So now there is this equation here, and so what is M? M is a positive semi-definite symmetric matrix, just a Gram matrix. And now I'm looking for the series of coefficients, so I'm looking for vectors alpha for which this equation holds. And once I find these equations, well, I find such an alpha, then I can construct the vector v, and for the vector v, this formula will hold. So if I would like to create a good unit vector v, or a good vector of norm root n now, then the only thing is that I have to estimate the L2 norm, or the Euclidean norm of these alphas. So now, these alphas are called inverse eigenvectors. Of our matrix M. So now the conjecture is the following, that if M is a positive semi-definite symmetric matrix, and don't forget that we started from unit vectors, it just means that the diagonal of M is constant 1, then there exists an inverse eigenvector whose norm is at most, well, we had n square originally, but after that I multiplied the vector by n, so now the norm is at most root n. Okay. So now if we prove this conjecture, then the strong polarization problem will follow from it. So the next question is that now how can I find the inverse eigenvectors of such a matrix? How is it possible? And now there is a very nice geometric way to do that. So what is the geometric way? Well, if I have a positive semi-definite matrix, I can just think of a symmetric ellipsoid as well. So take the ellipsoid E to be the set of those x's for which x transpose mx is n. and maximize, or rather locally maximize, the product of the coordinates on E. Okay, so what do we do? Well, we have this nice symmetrical ellipsoid. And after that, I just want to find the points for which this product is maximized. So what do? I take the level functions, so the level sets of these are hyperbolas. So I take hyperbolas, hyperbolic branches, which are tangent to my ellipsoid. And after that, if I take the contact points, then just by the same way as we got that this equality or this formula holds here, just by the same way, very simply, we get that the contact points or the local maximizers are the inverse eigenvectors of M. I write contact points. Okay. So immediately we get that if our matrix M is non-singular, that there are 2 to the n inverse eigenvectors, one in every orthant of the space. If the determinant of M is 0. And so now the question is, can we find an inverse eigenvector which is contained in the Euclidean ball of radius root n? So now, if we see when M is the identity matrix, then the ellipsoid is just the unit sphere of radius root n, and then we have exactly the sharp condition. So now the question: if I move away from the unit sphere, then is it still, well? So intuitively, one would expect that if some contact points are pushed inwards, then some will move outwards, and that would be basically the proof. Okay, so and for the polarization problem, the polarization problem would follow from the fact that there exists an inverse eigenvector for which the product is at most 1. Okay, so now what does it mean? Well, it means that if I just take the hyperbolide with the product 1, then there is a branch of this hyperboloid which does not intersect the ellipsoid. So that is the same. So now what do we know about the geometry of this problem? And there are two nice things. The first is duality. So if I have this ellipsoid E and I take the polar, and now with respect to root n times the unit ball, then this ellipsoid E star is defined by the equation x transpose M inverse x is n. Subject, well, of course, if M is non-singular. If M is singular, it is still possible to extend the inverse and have a good definition here. But so now, first of all, if I have my original ellipsoid here, then the dual ellipsoid will look like this. And so now if I had a contacting branch of the hyperbola, with product, say, alpha, then the dual will have the touching branch of the hyperbola with constant 1 over alpha. So the duality changes where these local maxima very nicely. And second, I have that the images of the inverse eigenvectors are the inverse eigenvectors of M inverse. Okay, so the duality that takes the inverse eigenvectors of M to the inverse eigenvectors of M inverse, and vice versa. So that will be very useful because also that is the same as the normal to E at an inverse eigenvector U is just U inverse. Okay, so that will be useful for us because we would like to move the ellipsoid a bit and use the argument of John, and for that we need the outer normals here. So that is a nice geometric property, the duality. And the other thing, well, just a remark, so what is the condition on the diagonal? But it is nothing, if you see it in geometric terms, it is nothing else but the intersection of the ellipsoid with the coordinate axis. Yeah. So intersection, so ellipsoid, well, root n times EI, so now EI are the coordinate directions, that is on the ellipsoid. Okay. So we have these two geometric properties, if you can say so. And so now there are several results that we could prove with basically the same technique. So I will just prove one. And that will be the following. So again, M is just as above, and it defines this ellipsoid E, and we take HE to be the hyperbolic shell of the ellipsoid. So now what does it mean? It just means that I take the union of these hyperbola branches that touch my ellipsoid. So this is the hyperbolic shell. And now the theorem is that if for any ellipsoid E tilde, which is inside this hyperbolic shell, and so now what I write is the trace of E tilde and trace of E. This is really just the trace of the matrix M. Yeah.
What's the definition of hyperbolic shell again?
So hyperbolic shell is the, so for you have this ellipsoid, and in every orthant of the space you take the hyperbola, where you take the maximum of the product of the coordinates, and after that you take the level set of the points for which the product equals that. So that will be a hyperbola. Yeah. And after that, for every orthant, I mean, of course, for different orthants you will have different constants, but you will have 2 to the m shells. Yeah. After that, you just take this union. And so now what I write there is so every ellipsoid E tilde which is inside this shell. Okay, so basically E tilde should be somewhere here. Yeah.
So every ellipsoid is disjoint from this.
Yes. Yeah. So it is better to. So it is really inside for which Well, it's not really disjoint, it's discrete, yeah? Because they're and now this trace of ellipsoid is just a trace of the defining matrix. So if the trace is maximal or locally minimal or locally minimal, then there exists non-negative scalar Ci such that M can be written as sigma Ci. Let's use alpha I tensor alpha inverse, where these alpha i's are the inverse eigenvectors of M. Okay, so in other words, I can write M as a linear combination, a positive combination of these tensor matrices. Well, now alpha tensor beta is just the m by n matrix whose ijth entry is just given by alpha I beta g. Okay, so now why is this true? Or, why is it good for us? Because if this holds, and we also assume that m is non-singular. So now if this holds, then I can just multiply by the inverse of m, and I get that the identity matrix is just sigma Ci alpha I tensor alpha I. And here, what is the trace of this? Well, the diagonal of this is just consisting of ones, yeah, because here I have alpha I, and after that here I just have the inverse of that. So the diagonal of this is 1, and I also know that the diagonal of this is 1, so it means that the sigma of the Ci's is 1. And now, if I come here, then what will be the trace of alpha I tensor alpha I? Well, that is exactly the norm squared of my vector alpha I. So now, just by comparing the traces, I get that there must be an alpha I for which the Euclidean norm is at most root m. So then we know that the strong polarization problem is true for m. Okay, so that is why this statement is useful, or that's what we want. And so now, what is the proof? So what does it mean that I am at a locally minimal trace position? It means that whenever I move my ellipsoid a bit such that it stays inside this hyperbolic shell, the trace will increase, or at least it will not decrease. So now, first of all, what is this ellipsoid E? Well, we know that M is positive, semi-definite, and symmetric, so it has a positive semi-definite or positive definite symmetric square root, what I denote by A. And now, this ellipsoid E is nothing else, just A inverse applied to the ball or the sphere of radius root n. So now, what will be my way of changing or modifying E? Well, instead of A inverse, I take A inverse times I plus delta H for some matrix H and a small positive delta. Okay. So now I modify this defining matrix a bit, but of course if delta converges to 0, then nothing happens. So now what is the condition? Well, there is no such H for which I stay inside the defining shell on one hand and the trace decreases on the other hand. So let's see first of all what will be the condition that we stay inside this hyperbolic shell. Well, it just means that for all the contact points I cannot, so if this was a contact point, yeah, so this was some alpha I, and I know that the normal vector here is just alpha I inverse. So it means that if I see what is the image of this alpha I, it cannot cross this bounding hyperplane. So what will be the image of my alpha I? Well, alpha I moves to alpha I times I plus delta H. And so now my condition is that the inner product of alpha I and alpha inverse should not be smaller, so it must be at least as big as the inner product of this. Yeah. So now I get that delta times alpha H alpha inverse. So I get that this must be negative. Yeah? And now this is just the same as the trace of H times alpha times alpha inverse. Or if we just take because the trace of two matrices is just the inner product on the space of matrices, so it is just the inner product of these two matrices. Okay. So we get that this inner product should be negative for every I. Yeah. So this is one condition. And the second condition is that we have to take care of the trace. And now let's see what happens to the trace of our matrix M. Well, so M is now what it will be? Well, it will be I plus delta H inverse times A. Well, A is symmetric, so it is AA. And again, inverse. And now, of course, as delta is very small, I'm really interested in the derivative of this with respect to delta. And so that happens to be about trace of M. So this is about I minus delta H. So this is about trace of M minus, well, 2 times delta times trace of HM. Because here we use that the trace AB is just trace BA. So now, what is the condition? That the trace of M tilde should be less than the trace of M. So now it means that the trace of HM is non-negative. Yeah? So now what do we get? Our two conditions is that there is no such matrix H for which, and now this is the same as the inner product of H and M. So there is no such matrix H for which this is non-negative and for which all of these are non-positive. And after that you get that now if, so just by the separation theorem you get that it must be the case that M is contained in the convex hull of these matrices. The positive hull, sorry. Because otherwise there would be a separating function, and that is our choice for the matrix H. Yeah? So M can be written, so M is in the positive hull of these tensor matrices, And now what does it mean? It exactly means that there are positive constants Ci, non-negative constants Ci, such that M sigma Ci alpha tangle alpha inverse. Okay, so we get that if we have a locally extremal matrix, then the strong polarization problem holds for that. And so now the conjecture, which is the inverse spectral conjecture, is that this holds for every matrix which are positives and symmetric, and they have one on the diagonals. And now, of course, it would be enough to prove it that actually the set of these locally extremal matrices is dense in the space of the matrix, because then you would have the statement already. But I don't know if it is true. Okay, thank you very much.